Hello, this is Britt Caswell with another example video. In today's video, I'm covering example 3 from section 7-5 in the SavvasRealize Algebra 2 textbook. The goal of today's video is to graph y equals a times the tangent of bx. So understand this is without any translations, right? This is all stretches and compressions in the vertical direction and the horizontal direction. Now remember from our last video that the period of the tangent function is pi. Alright, see here how it goes 4 boxes, and 4 boxes is from 0 to pi. So when we are dealing with this, the hardest part for students is this number in front of the x. You just take pi and divide it by that number. Okay. So let's start with this 2 times the tangent of 4x. Alright, what I have here is I have the parent function of the tangent, just so that we can see it and know what it looks like. And so the tangent function is difficult for people because it is centered at the origin, as opposed to starting at the origin and moving on. And so, because it has a period of pi, it goes half of it on one side of the axis and half on the other side of the axis. So just be aware of that when we're talking about this. Okay, so now the 2 is describing a vertical stretch, right? You guys know that with a function at pi over 4 and at negative pi over 4, the tangent function is at 1. So instead of being at 1, it would be at 2. Okay. So that's what that 2 is doing, is it's just kind of stretching our graph, so it's going to be a lot steeper, something like that. Okay. So now the 4x. The 4x is where things get a little ugh. Okay. So let's start with the period. So the period of the tangent function is going to be pi divided by that 4. So the period of this function needs to cover 1/4 pi. Now here's the thing. We know that half of that function is going to be over here and half of it's over here. So what I want to do is I want to cut my axis into eighths of pi, which I know sounds like a pain in the butt, but let's just try it out with me, okay? So here's pi. There's half a pi. There's 1/4 of pi. That's 3/4 pi. And so that would be pi over 4, but I want eighths. Okay, so here's pi over 8, 3 pi over 8, 5 pi over 8, and 7 pi over 8. And I want to do that backwards as well, so I'm just going to mimic those. I think I'm good enough as far back as I've gone. I'm not really focused on the negative aspect of it, more of the positive and getting that swoop in there, okay? I'm a little neurotic though. Here we go. There we go. Anyway, sorry. So there I've cut my axis into eighths of pi. So I'm super zoomed in here. Actually, it's about the same as this one. That's okay. So now let's go ahead and let's graph this. So I know it's a period of pi over 4. And so pi over 4 is 2 tick marks worth of stuff. So if I'm centering 2 tick marks worth of stuff here, I know I'm going at pi over 8 and negative pi over 8. So there is going to be my first swoop. And so every 2 tick marks is pi over 4, so got a little wild there at the end there. So what I'm doing is every 2 tick marks, I'm putting another iteration of the asymptote. Tangent graphs are heavily dependent on asymptotes in order to make them understandable. So that's why I'm so careful about them. So as you can see from my sketch here, I'm going to have just a ton of these things. So on my parent graph, from negative pi to pi, you can see it happens once, and then if I piece those halves together, I have a tangent swoop twice. So on the parent function, I have 2 swoops. On my adjusted one, where it happens 4 times, I should have 8. So here's 1, 2, 3, 4, 5, 6, 7, and then a half makes 8. So that's why there's so many of these, because we have 4 times as many of them happening in the same interval. Okay. So now to get my zeros, all right, my zeros are going to occur at the halfway markers between these swoops. So those are very conveniently marked and labeled. I'm just going to go ahead and put them in there. So halfway between each of these, I'm just putting a dot. I guess I could put them there and there too. All right, now remember, on our parent function, we go up 1 at pi over 4. So like halfway between my 0 and my asymptote, it goes up 1. So on these ones, halfway between my 0 and my asymptote, it's going to instead go up 2. And so that's what's going to happen here, and it's going to make this thing super stretched out, like this. And all of these will appear that way. So halfway between and halfway between, like that. And so I'm kind of drawing these in here, not very well because I don't know how to draw. They're getting a little worse. Remember, they are kind of like that nice S shape, but they're very stretched out S shape because of that vertical stretch. And so what I have under that red box there, what I have under that red box there is I have the Savvas picture of it, which looks a lot nicer than mine. And so I'm going to put it up. I just wanted you to see where these values are coming from by sketching it by hand. There we have that. So now let's delete this picture. I'm also going to erase the graphing stuff I put over it so you can actually see the graph. And so see, now they're doing it, but their axis only goes by pi over 4ths instead of 8ths. And so you could tell that there's an asymptote halfway between there, but they don't draw their asymptotes in there, and I think that makes it a little less clear. So there we are with the tangent function. So now let's try it with the cotangent. Now this cotangent one is more difficult because they have a 3 in front of the x. That means that we're dealing in thirds and then half of thirds, which makes people really uncomfortable. And so here's our parent function of the cotangent. Now notice the cotangent is really nice because it goes from 0 to pi. And so when we're cutting this up, it's a little less intimidating. All right, so I'm also going to cover to negative pi and to pi. Because I'm going to be dividing my period into thirds. All right, I'm dividing this pi into thirds. I'm going to go ahead and do that first. So that's going to be with my asymptotes. So there's pi over 3 and 2 pi over 3. So those are where my asymptotes go, right? Now, the struggle here, where we kind of encounter our struggle bus, is that our cotangent function has zeros halfway between these. So not only do I have these third things, but I need to go ahead and I need to put tick marks between them in like the 6th positions in order to get my halfway markers. Alrighty, so there's my asymptotes. So you could see that where 2 swoops would normally happen, now I have 6 swoops happening. Okay, that's what that 3 does, right? Because the period equals pi divided by 3. That's where I'm getting that from. Alrighty, so now I need those middle markers, right? And so these are the 6. These are the pi over 6, because that's half of pi over 3. And here's pi over 2, because it's halfway between 0 and pi. And then this one would be 5 pi over 6. I think the hardest part here for most students is the fractions, actually. Most people aren't super strong with their fractions, and then they get nervous because there's a pi in their fractions, and that just kind of freezes them up a little bit. If you wanted to, you could label all of these in terms of 6. So this could be 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. That might make you feel a little bit better because it has that counting feature on it, and I think that helps as well. I just have the reduced versions of the fractions. Alrighty. So we have dealt with the 3x. Alright, we know we're going to have a bunch of swoops coming down like this. Okay, and they're going to intersect at these black points. So the other thing to consider is this 1/2. So what this is saying on our parent function is that right here at pi over 4, it's at 1. So halfway between the 0 and the asymptote, our graph is at 1. But we don't want it at 1 anymore. Now we want it at 1/2. So what we're going to do is we're going to have a vertical compression to where halfway between my 0 and my asymptote, it only goes up to that 1/2 marker instead of the 1 marker. So there's my zeros. And so when I go to draw my anchor points for these, I go halfway. And so that's at the pi over 12 marker, which is like, ugh. I don't like it. I think that it's a little hectic. And so that's why Savvas is really saving the tangent for last, because if they did the tangent first, I think y'all would have had a heart attack, just to be honest with you. Alright, so I did those anchor points, right? Halfway between each intersection point and the asymptote. And they're each at 1/2 instead of 1. And now I'm going to just draw in my swoops. And so I have the Savvas picture of it as well, and I'll show you what that looks like as well. Just remember, the cotangent and the tangent, they end up running along those asymptotes, right? So these are getting closer and closer to those blue lines, but never touching. But y'all, I can't draw. The other thing is that when we get to such small increments, people tend to shut down because there's so much going on the graph. It might help you to just draw one iteration. Oops. Like, you could just focus on this one between 0 and pi over 3, and then just copy it afterwards. I'm not sure. I don't know what is honestly better. So I'm just clearing kind of a spot. And so here is the Savvas picture. So see how I was reminding you that it was at pi over 12 on this anchor point? Because it's halfway between 0 and pi over 6. That's where they're getting that. And the 0.5 is the 1/2. So that's where they put their 2 anchor points. So when they graphed this, because it's only like the little sliders or the 2 anchor points, they just focused here, and then the graphing technology produced the rest of it for them, which is kind of nice. So there we have it, guys. That is graphing A times the tangent of B. BX. Until next time.